we can get an idea for how much carbon dioxide is being generated by combustion of fossil fuels by looking at the chemical reaction. This chemical reaction gives us the relationship between number of molecules of this fuel burned and the number of carbon dioxide molecules that are released. So if we have we get 16 carbon dioxide molecules for every 2 molecules of octane. So if we went around the globe and counted the number of octane molecules, we could figure out how many molecules of carbon dioxide. Is that practical? No, we can't count molecules. Moles, 16 moles of CO2. So this was 2 molecules made 16 molecules. Remember, mole is a counting unit like dozen. We could also say 2 dozen of this gives 16 dozen of that. We're just multiplying everything by 12. So we can also say 2 moles of this, 2 chemist dozen, would produce 16 chemist dozen of this. The amount of the substance used, each and every one of them in that reaction, and the amount of substance produced are all related to each other. So we have the law of conservation of mass. The mass of what you start with equals the mass of what you end up with. We don't have things being created or destroyed. And this is also related and why we balance equations by balancing the atoms. Chemicals react based on numbers of molecules and atoms. It's particles, and it's exact. This many atoms to this many atoms, they'll combine and form a specific number of molecules. And here's a fun word, stoichiometry. Stoichiometry is the study of the numerical relationships between chemical quantities. And so that's what we're going to look at. Come on, next page. There we go. So the coefficients in that equation, it has to be balanced, are going to give us relative amounts in moles. So we kind of already said this, but we can elaborate. 2 molecules plus 25 molecules gives 16 molecules and 18 molecules. Or we can say moles. 2 moles of that reacts with 25 moles of this, creating 16 moles of that and 18 moles of that. We could express it as a ratio. Now suddenly, we're going to talk about pizza. I know, maybe you're getting hungry for lunch. Chemical reactions have a lot of things in common with recipes. Okay, how do you make a pizza? Well, you could do it different ways, but this is one way. 1 crust, 5 ounces of tomato sauce, 2 cups of cheese gets you a 1 cheese pizza. You know, if you're making pizzas for Papa Murphy's or something, they want you to specifically put a certain amount of cheese on there, right? They don't want people to complain that they're not getting enough, but they also don't want you to be giving away too much cheese. So it's a specific amount. And we can express this mathematically as well. 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. It's a ratio, a relationship between the amounts. And we can use these to calculate how many pizzas we could make. Because let's say, what if we had 10 cups of cheese? How many pizzas could we make, provided we had plenty of anything else? Well, we can use these things as conversion factors. Okay, we know that we need 2 cups of cheese for every 1 pizza. We get 1 pizza for every 2 cups of cheese. That makes a beautiful conversion factor. So we've got 10 cups of cheese, we multiply by this conversion factor, and we see that we could make 5 pizzas. Now, most of us could figure that out in our heads. It's important to see how the process works, because when we go back to the octane burning and the carbon dioxide, people lose their brains. Okay? It's the same thought process with pizza and with the compounds, the chemical compounds. But some little switch in your brain freaks out. So try to not let that switch flip. So the coefficients in the balanced chemical reaction act as conversion factors. That chemical equation allows us to convert between moles of any two reactants and or products, any of them, in one step. It's beautiful. So let's look at this. If we burned 22 moles of octane, how many moles of carbon dioxide would be formed? Well, let's look at the reaction. For every 2 moles of octane that we burn, we get 16 moles of carbon dioxide. 2 moles of octane per 16 moles of CO2. So we're doing dimensional analysis. We're told that we're burning 22 moles of octane. We want to multiply by what they're asking for, moles of carbon dioxide, and we're going to divide by moles of octane. These numbers are the coefficients in the equation. So here we have the 2 moles of octane, that goes right down there, and 16 comes in here. You put the units in, you look at the balanced chemical equation, you pull those numbers in. You do the math, just like converting centimeters and millimeters. So from this we find that burning 22 moles of octane would add 176 moles of carbon dioxide to the atmosphere. Now, we don't measure things in moles. Those balances back there don't measure things in moles, do they? No. We measure things in grams. And so we need to relate this to a quantity that we can actually measure. Because mole is a counting unit, and the way we count atoms is by weighing them. So here's our general conceptual plan for stoichiometry. Usually we measure things in grams, but it doesn't have to be grams. So here we have Dora the Explorer, and her little chant is going to be the same. Grams to moles to moles to grams. Okay, and if you did not learn that in your previous chemistry class, now's the time to learn it. You should wake up in the middle of the night, grams to moles to grams. Okay, that's the centerpiece of stoichiometry. We'll do little variations on it, but that's the go-to path. Grams to moles to grams. We will be given a mass of one reactant or product and asked for a mass of another reactant or product, like talking about CO2. Well, we could figure out a rough estimate for the number of grams of fossil fuels that are burned annually, right? So grams of octane. And we could figure out, using stoichiometry, the grams of carbon dioxide that would be released into the atmosphere as a function of that. Grams of octane will convert to moles of octane, to moles of carbon dioxide, to grams of carbon dioxide. So let's do that. So U.S. Department of Energy says that the world burned approximately 3.1 times 10 to the 10th barrels of petroleum in 2010, which would be equivalent to 3.5 times 10 to the 15 grams of gasoline. So calculate the mass of carbon dioxide emitted into the atmosphere using the combustion of octane as the representative equation. This is not going to give an exact number. None of these numbers are exact, are they? This is an estimate. This is an estimate. Gasoline is not pure octane, but we have to start somewhere, right? So this will give us an estimate. And then we're going to compare this result. They're telling us volcanoes produce about 2 times 10 to the 11th kilograms of carbon dioxide a year. I know, right? I'm sorry.
It's very annoying.
It is very annoying. She is very annoyed because she's trying to do lab over there, and some of the stuff she needs is in this room. It's life. Okay. So what we're starting with, let's see, where is this? Is we've got grams of gasoline, and we were asked to find the mass of CO2. So grams, and we're told, well, let's just assume that it's octane. So grams of C8H18. That's where we're starting from, and we want to end up with grams of CO2. So what do we chant? Grams to moles to moles to grams. So our path is grams of octane to moles of octane to moles of CO2 to grams of CO2. Once we establish the big picture, then the rest of it is putting little pieces together. If you don't know where you're going and have a plan on how to get there, this becomes really difficult. Okay? But when you see the big picture, it is not that difficult. Okay, so we're just going to use dimensional analysis and set up this equation. So we're going to start over here. We've got grams. We're using 3.5 times 10 to the 15. That's a lot of grams. C8H18. Oh, something else I'd like to point out here. In this transition from grams of octane to moles of octane, the unit is changing, grams to mole. The compound is not changing. And in this last one, moles of CO2 to grams of CO2, the compound stays the same, the unit changes. In the middle, though, the unit stays the same and the compound changes. You can only change one thing at a time. You can't change the unit and the compound. So we've got grams, and we're going to have 3 conversion factors. Let's see if I can space this out, get it in here. Times, times, times. Grams of C8H18 to moles of C8H18. I know it's a little tedious, but write the chemical formula in there, because otherwise you'll end up in this middle one with moles and moles, and it's easy to put the wrong numbers in. Grams of CO2. Grams octane, moles carbon dioxide, grams carbon dioxide, following our path. Then we put units in so they cancel out. We've got grams, C8H18 down here. Those cancel. Moles, C8H18. Those cancel. And moles CO2. Put the units in first. The units tell you what to do. You learn this process called dimensional analysis, and it greatly reduces the number of equations and processes that you have to remember. Now we need numbers. This middle term, moles of one thing to moles of another thing, comes from the balanced chemical equation, which is no longer written on this slide, so I'll put it up here. It was 2, correct me if I make a mistake on this. It goes 25 oxygens and 16 CO2s and 32 waters. Is that right? Anybody have notes? Is that good? I know the 2 and the 16 are correct. 18 what?
Water.
Oh, sorry. Better? Okay. So this middle term I like to do first because it's easy. So moles CO2. All I do is I go to the balanced chemical equation and I find CO2, what number's in front of it? 16. So then down here in front of CO2 I write 16. I need C8H18. I find it in the equation. There's a 2 in front of it, and so I put a 2 in here. You've got your balanced chemical equation. You find the compound you're interested in. What's the coefficient? Write it in front of that in your formula. Don't make it harder than it needs to be. Now, what are we going to do here? How do we convert grams and moles? Molar mass. So we need to calculate the molar mass. So for octane, it's 8 times carbon and 18 times hydrogen. Eight times 12.01 plus 18 times 1.008 equals 114.224. Let's just think about significant figures real quick. What's probably going to limit the number of significant figures in our answer? The grams of gasoline. Because this only has 2 sig figs. Okay? So if I rounded this to 4 significant figures, I would still have 2 digits more than I need, right? So I'm going to go ahead and write the whole thing down, but you can kind of think about this, and if your starting number is so estimated, then you don't need to be as super careful here, and we should all end up with the same number anyway. So 114.224. And then I need the molar mass of carbon dioxide, 1 carbon and 2 hydrogens. Sorry, 2 oxygens. Like, that's not 40. I know it's 44, but that's not adding up. Good grief. Oxygen, okay. I think that's 44.01. So over here, that number always goes in, it's the grams. Remember, the molar mass is the mass of 1 mole. Okay, 3.5 EE 15 divided by 114.224 times 16 divided by 2 times 44.01 equals. This is my final answer, so I'm going to round it to 2 significant figures. 1.1 times 10 to the 16th grams of CO2. That is the mass of CO2 emitted. Any questions? Now we're asked to compare that result to the amount emitted by volcanoes. This is grams, that's kilograms, right? So let's convert this to kilograms. We would multiply, I don't have space, we would multiply by kilogram over 10 to the 3rd grams. So this is going to be 1.1 times 10 to the 13th kilograms of CO2. So how does that compare to the amount of CO2 emitted by volcanoes? It's more. How many times more? About 100 times, right? This is 10 to the 11th, and this is 10 to the 13th. So about 100 times more. So just based on this really rough calculation, if CO2 is causing this increase in temperature, is it us or the volcanoes? It's more likely to be us, because we are putting out more than the volcanoes are. Now, are these perfect calculations? No. A lot of this stuff necessarily has to be estimated. Any questions?